Hello, very good morning. Very good morning to some, very good afternoon to some others in Europe. So welcome. This is the second session of the day regarding this session for looking at the use of discrete analyzers, the SmartChem analyzers, for the test of heavy-duty engine coolants. The idea throughout the day will be going through a specific agenda that I will be happy to show, but seeing that the number of attendees may increase, let's give them a couple of minutes. In the meantime, let me say this will be a very open session in the sense that you can post your questions at the chat and you will be able to get your answers at the end of the session or throughout our specialists in your specific territories. Let me please introduce myself. My name is Roberto Marcos Perchin. My background is a MSc in physical chemistry and operations, and I am the business development manager for AMS, which is a KPM brand. So I said, let's wait for a little bit to see if more people join us. And otherwise, we can kick off. So we will let people join through because it's past the time, so we can kick off. So let me please stop my camera and we can start going through the specifics. So I said the idea for today is talking about the determination, in this case, of nitrites in coolants. So we will take a look at the existing techniques. We will look at one of those techniques, discrete analysis. We will talk about the concept of discrete analysis and particularly the SmartChem platforms. Then we will look in detail how the application of NO2 testing takes place in discrete analyzers. And then we can look at what other parameters can be tested on SmartChem discrete analyzers, and we can finish with a discussion and a Q&A session. As said, any questions you may have, please post them on the chat, and we will see answering as many of them as possible at the end of the session. So let's start by defining what coolants, or as known in the US, antifreezers, as they have a very important role and they have a very important impact due to the quality and maintenance in terms of engine failure, which is also related to lubricant failure. The main formulation of coolants is glycol, water, and an additive package. This additive package will differ from formulation to formulation, brand to brand, and especially the very application of the coolant itself. Let's look at these formulations, have different missions, and amongst these missions, the key point is to prevent corrosion and improve efficiency of the engine. Hence, we're looking at improving the lifespan of those engines, of those components. One key element of these additives is the presence of nitrites. Why nitrites? It's because they actually help in the prevention of the pitting of the cylinder liner, because what they do, they create a protective layer. What they do is actually they get this coating that actually helps preventing that pitting corrosion. We have to understand that in the inside of the cylinder around the liner, it's very high pressures due to the combustion. Of course, we're trying to prevent that pitting from taking place. So because we're creating that protective layer, we're creating that special layer of protection, the nitrite concentration will be depleted over time. Because of course, as long as this layer is breaking down because of the nitrites, it needs being replenished. So at a certain point, the nitrite concentration will be below a certain level, which is considered a secure level, and it means that the coolant needs to be replaced. So at what point should one replace that coolant? It is due, and it is looked at by virtue of looking at this specific testing. One has to check the nitrate concentration, how it's being depleted. When it reaches a certain point, the replacement of that coolant is going to prolong the lifespan of the components of that engine. And also, if exchanged too early, is going to have an impact because the coolant was still in good condition to work. So how can we run this kind of test? We're going to look at the most common methods. So we're going to take a look at those existing techniques for nitrite testing in coolants. The first one, the oldest one, and also the easiest one that one could imagine is through a standard colorimetric indicator titration. This is a very manual technique. We all know how it works. It's our usual glass burette. Our titrant in the glass burette, in this case, they are cerium 4 salts, and using a colored indicator, ferrine, and we perform an endpoint titration. And we all know how it works. We start swilling a beaker with our sample in and start dispensing titrant until we see that changing in the coloring. In this case, additionally, this technique requires an acidification, so pH adjustment is required. And we know that repeatability-wise, this technique is very operator biased, it's very manual, and depending on the skill of the operator, it can be lengthy, it can be shorter. But very specifically, one has also to look at the measuring ranges because we're talking somewhere between 10 and 60 ppm, what means not a very precise technique when one is looking at lower ranges or lower concentration than 10 parts per million of nitrites. Next one we can look at, very common in many laboratories, is ion chromatography. Ion chromatography is a very common technique for the determination of anions. Nitrite is an anion, and in this case, it's based on the separation of the different anions throughout column and then the detection of the very phases coming out of the column at different times. In this case, the detector will be conductivity and suppressor is required. So how do I build my ion chromatography technique? Is the usual. I get my ion chromatographer, I have to get my column, I have to inject my sample also with an eluent. I need also to take into account column regeneration. So I need reagents. I also have to take into account the suppressor recycling solutions because it has a specific universe to take into account. And very importantly, I'm not only measuring nitrite, although my key target is nitrite, I have to take into account I will be measuring other anions throughout the retention time of the column. So it has a point that has to be taken into account that it imposes a certain test time per sample because of that column retention time, which typically will be in the 15-minute range. And we will see this later in a minute as well. So for nitrite, this would mean measuring a bunch of other anions plus that time per sample, which is 15 minutes. In case of automation, yes, we can do it because we could actually load our samples onto an auto sampler. Of course, it's very common to see coolant testing for certain analytes, but nitrite to be run on ion chromatography because certain analytes need to be run on ion chromatography, such as glycolates, but glycolates are not in common with nitrites on the columns. So even if I were measuring glycolates, I would not be able to measure nitrites because they require different columns. The other one, moving on from conductivity detection onto spectrophotometry, visible in this case, but also known as colorimetry, is our typical visible spectrophotometer, manually operated. In this case, what we would do is run our tests based on specific reagent, sulfanilamide, pardon me. We would use the method actually is the SM4500 NO2B which requires an absorbance at 543 nanometers. So what we would have is we would work pipetting and going through our cuvette and manually loading it onto the spectrophotometer and taking the reads, of course, in terms of absorbance, or loading our calibration curve in advance and doing it one by one. Taking one step further, what can be done is use a discrete analyzer. So what is a discrete analyzer? If you allow me the expression, it's a spectrophotometer on steroids. It's a fully automated spectrophotometric visible platform that will run all the steps required for the spectrophotometric measurement to be run. So from reagent blanks, sample blanks, calibration, QCs, sampling, everything is done automatically. So in the same way that we were seeing of a manual technique, we would be using the same methodology on the SmartChem analyzer. So what we were running is our sulfanilamide method based on the SM4500 NO2B and absorbance at 543 nanometers. So very common is to see different platforms. So let me show you, for example, one that is very well known. It's our SmartChem 200 analyzer. And actually, it takes part in multiple videos from companies such as Caterpillar, where they have their SOS service and they test nitrites on a continuous basis. So in this case, actually, you can see two analyzers working in parallel, because you have the one this gentleman is actually inserting, in this case, samples on, and on the back, you can actually see a second unit running. So this is a system that is very, very well trotted in terms of running these tests, but not the only unit we have working in this way. So, of course, one would have the question, okay, what is a SmartChem discrete analyzer? How does it work? How does it run? So let me start from the main principle. And the main principle of these units is visible spectrophotometry, also known as colorimetry. So in this case, if we take a look at the SmartChem 450 measuring principle, is working with a light source that will work on a filter wheel, on filters mounted on a filter wheel. It will go through a reference detector, take a reference reading, and through the solution to a sample detector, and will give us an absorbance. That absorbance, of course, will be taken into account that it's not a net value, it has certain points and elements to take into account. If we look at the principle of a colorimetric reaction, is that one would start with an empty cuvette, add the sample. At this point, the absorbance of the sample would be checked. So the background absorbance, some people call it sample blank, would be measured. Additionally, the reagent would be added, either 1 or 2 or 3 reagents, because different reactions would have. In the case of nitrite, it's a single reagent addition. There would be an amount of time for color development that would lead to a specific color. At that point, we would take a spectrophotometric measurement, and by virtue of the Lambert-Beer law, we would take our concentration. We would have an absorbance that actually can be related to a concentration via calibration curve. At this point, what are the elements comprising a discrete analyzer? So if we take a look at the specifics, what we will have is literally a way to replicate the whole laboratory onto a platform. So the first thing we will have and the first thing we will receive will be our samples. So we will have a sample bay. Somewhere we are storing our samples ready to be run. So in other words, it would be our autosampler. This is where we would load our samples waiting to be tested. As we said, we need to add reagents to those samples. So we will have a reagent bay. And that reagent bay and that sample bay will be communicated with the reaction area through an aspirating, dispensing, and mixing arm. That arm will take the sample and dispense it onto a cuvette. The reagent then dispense it onto a cuvette. So those cuvettes will be on a ring, mounted on a ring. And that way we will have a multiple stack of cuvettes. So we will have, in this case of SmartChem 450, sake of argument, we will have a rack of 80 cuvettes sitting in a reaction area, which actually is thermostated at 37 degrees C. So that way we will have a faster kinetics of reaction, increasing the speed of the reaction, hence reducing the time for total test. As we said, at a certain point, a cuvette will reach the point at which the color has been fully developed. At that point, that cuvette will be transferred to be read by the spectrophotometer. And then once read, that cuvette will be deemed ready for being washed. So at that point, the cuvette would go and travel to the wash station, and onto that wash station, by having some wash and rinse solutions, some supporting solutions for the wash, including distilled water, that cuvette will be washed, and it will be deemed ready for the next reaction. Important points, because we were comparing this technique to the manual technique because of the automation. Is not just the automation, because whilst in manual testing we're running in the ranges of milliliters, a SmartChem Discrete Analyzer is working in the range of microliters. So it means that samples and reagents will be dispensed in order of magnitude of microliters. This also means that the only waste generation from this instrument will be coming from that reaction, will be volumes of reagent and sample in microliters. Additionally, we could also split the very waste into hazardous and non-hazardous waste lines. And as in the case of SmartChem, we are not using disposable cuvettes. There's no need to have to deal with hazardous waste, including solid waste, because of potential hazardous materials being actually as liquids within the cuvettes. If we take a look more in detail, what we have is again, I'm using the SmartChem 450 for the sake of this session, but of course it can differ for systems such as the SmartChem 600, and we'll be happy or either to explain or our specialists can get in touch with you. So there's a sample bay that also allows for continuous loading. The sample bay works with circular racks of 15 or 18 position each. Then the reagent bay is right next to it, and it's working with 50 ml or 25 ml bottles, of which some can be barcoded, because with SmartChem we have some ready-to-use reagents which are barcoded. The dispensing arm that connects everything onto the reaction bay, and the reaction bay has a circular rack of, in this case, 80 cuvettes. Here we can see a technical polymer cuvette with a 10 millimeter optical path. So with this is what gets in here. Once the cuvette has run its reaction, has been read by the photometer, it goes through the washing station that takes care of the full wash and the drying in the cuvette, making the cuvette ready for the next reaction to take place, for the next test to be run. So because we have, in this case, 80 positions, we are running what's called parallel testing, because it's going to have an impact on the turnaround time. What does it mean by parallel testing? We're going to see it in a minute, but it's very important that the testing can be run in either batch or into random access mode. By random access mode, I mean that the system takes a look at the tests it has to run and decides the most efficient way to run them, which might not be into specific batches. By batch, it would mean that I would run first all my nitrites, and then, for example, I would run my phosphates all at once. So I would be running one, and then the other method, and then the next method. in a random access mode, it would be a mix that would be defined by the system. Additionally, not only could I expedite priority methods, I could also define express samples. So I could define that samples A, B, and Z need to be the first ones to be run, regardless of not being the samples 1, 2, 3 position. So I could also take into account that there could be multi-matrix or multi-solvent loading, and multi-range method can be loaded. But taking a look at this parallel testing, as we were saying, is what we have is a system that, if we remember from a previous slide, we have the sample, we have our reagent, and there can be a waiting time from reagent 1 maybe to reagent 2, or there can be a waiting time because of that incubation time. So it means that the system is free to run other activities in parallel. So what the system does is it will load one position, and automatically, with the time it has before having to take action onto this position 59, it can start running the loading of additional positions. So it means that instead of having to wait for a lengthy amount of time for that incubation to take place, it goes far faster, because we're seeing that we can get results between 15 to 30 seconds between samples once that first result has taken place. And we will see this in context in a minute. So if we look at this, for example, this is a 40 test batch where we have run four samples. We have decided to run 10 replicates of each. And what we see is that the time to first result is 7 minutes. That's exactly the incubation time it's going to take. And what happens is after that first result, because after that first result, what we are getting is results approximately every 30 seconds. It means that we're going to get a total testing time of 28 minutes for those 40 tests to run. If I were using ion chromatography, sake of argument, because we were talking about it, about another automated technique, within 28 minutes, I would not even be able to get 2 results, because we were talking that in this case, for example, we would be looking at a column that would demand 15 minutes as turnaround time. So one could see immediately the difference between running ion chromatography versus discrete analysis in terms of the automation would be comparable, but the turnaround time would be completely different. So I would be able to run as many replicates as I would like without having to worry about all that waiting time. So if we take a look at the specific testing for nitrites, we would be looking at, by the way, this is the way the system looks in any laboratory. We would be looking at that colorimetric reaction. So we said this is based on SM4500NO2B, where, as we said, we empty the cuvette, we add our sample, where we actually have to add diluent to fill up to a certain volume in the cuvette. And then after letting it mix, we can actually add our reagent. In this case, you can see that we're talking about 100 microliters around. So 150 microliters of sample, 110 microliters of reagent. In this case, as we said, sulfanilamide. So after this, we have a waiting time of 362 seconds to get to that color development, to get to that incubation. And from there, once the color is developed, we move the cuvette to the spectrophotometer. We run a reading. As said, previous to this, we have measured our background absorbance, or as some people call it, sample blank. And of course, we already have a measurement of our reagent blank. So that way we calculate our net absorbance. And from there, we calculate our concentration, because we can actually plot with our calibration curve. But this is only nitrite. So can we measure other parameters? So pretty much anything that can be measured colorimetrically, with a few exceptions because of some specifics in the reaction, can be measured. So we could be looking at parameters such as hardness. We could be looking at alkalinity, calcium nitrates, importantly, chromium-6, chloride, calcium, potassium, cyanides, copper. So it's quite a long list, but they all can be implemented through different reactions. And of course, the advantage is that one can define the starting one day with nitrate alone, and the very day after, decided to add any of those, be it ammonia, nitrate. Of course, after digestion, things like TKN, TN, TP. Of course, total nitrogen can also be calculated from TKN plus TON, so nitrates and nitrites. And one specific thing I can mention is for nitrates is that this system does not have interference because of chlorides, because of course, if not working with hydrazine, of course, working with a cadmium column reduction or with vanadium chloride, chlorides don't pose an interference to the method. So as a conclusion, what we can see is that the use of discrete analyzers for nitrite testing in coolants, what is going to allow is to optimize resources, both human and financial, because looking at some automated techniques, fully traceable techniques, fully repeatable techniques such as ion chromatography, there's a very high difference in terms of OPEX. And of course, is going to have a specific point because it's going to be full with regulatory compliance. As we said, SM 4500B. So depending on the sample, though, depending on the testing throughput and requirements, these SmartChem systems, we are actually allowed to range from 60 to 200 sample positions. So we're going to have the ability to load up to 200 positions for samples, in this case in the SmartChem 600, or 60 in case of the SmartChem 210, with an intermediate value of 100 for the SmartChem 450. So if you allow me, this shows these platforms are quite flexible, not only in terms of the throughput, nor in terms of the operator, but also in terms of adding additional methods, adding also specific methods for specific ranges, because it allows multiple calibration points or multiple calibration ranges. It's a full walk experience. The idea of these systems is to let the operator load and leave. We have seen that reduced impact in the waste generation, both because of the volume of the reagents and samples being in microliters, but also because it's not disposing of any consumables such as used cuvettes. Also, we see it's a very efficient tool for laboratories, allowing that complete automation. Somewhere that of this session can be discussed with our specialists or with ourselves is the possibility to run pre and post dilution routines for the samples. So they become a very natural step for laboratories for running their inorganic ionic testing. So once again, thank you very much for your time and hope to see you in next sessions. Thank you.